Hello everyone and welcome back to another in-depth concept, this time about calculus and limits at infinity. So like I said in the intro to this topic, basically limits at infinity are different from the regular types of limits because we can't substitute infinity immediately. And we can't also just use arithmetic logic with infinity because like I said in the last video, infinity is a concept. Infinity doesn't exist. Even if I say that there's an infinite amount of, let's say, stars in the sky, there is still a number. And infinity is basically just the representation or the conceptual representation of an ever growing set of numbers. So, how do we describe limits if it's approaching infinity when infinity isn't even really a number? Limits as it approaches infinity are easily described by for example a graph. If you guys wanna like use graphical analysis, it's easy to describe their limit when you see, for example, um, a function that goes like this. A function that goes like that is essentially, hold on, something like this. Let's change the color of that. Function like this goes on infinitely to the right and infinitely to the bottom. Now, we want to see where it's going in terms of the y-axis as it goes to the right infinitely. So since there's essentially a horizontal asymptote here, right there, pretty much what we're getting is the y value of the horizontal asymptote. So let's say that this is going to be 3. Our limit is 3. Okay, now about that. Limits at infinity describe asymptotes. And if there is no asymptote, can we say that there is no limit at infinity? Well, we will see. To recall how to get the horizontal asymptote of a function, let's try recalling a simple concept. So let's say we're given a rational function. We're given the question x squared plus 16, for example, over 4x squared minus, I don't know, like 2. We don't even have to really solve the entire thing. We don't have to put our infinity there. What we can do is get the horizontal asymptote using our GenMath knowledge. Now, GenMath, what is taught to us in most schools, actually in the most basic curriculum, is that there's a condition here. For any rational function where there is a number with the highest degree, um, let's use a here and b. Okay, there. And there is a coefficient here. Sorry, the line is so long, I'm getting OCD. Let me fix that. Okay, consider this example. According to GenMath, basically, if the degrees are equal, if n and m are equal, is equal to m, then the horizontal asymptote is equal to a divided by b. So their coefficients divided by one another. Now, if n is less than m, the horizontal asymptote is 0. And if the numerator is greater than the denominator, then that means we have no horizontal asymptote. So there, equals does not exist. Now, how do we use this logic now? How do we use this in this type of equation or expression rather? So, remembering this, if n is equal to m, the horizontal asymptote is equal to a over b. And we know that the limit as x approaches a certain infinity is going to be equal to the horizontal asymptote. So, all we have to do to get the limit of this function as it goes towards infinity is to get the what's it called? The result of dividing the coefficient on the top of the highest degree term and the coefficient of the highest degree term on the bottom. here we can see that our highest degree term is x squared on both sides. They're both up to degree 2, so that means we're satisfying this condition right here. So we want to get their coefficients. This is 1 and this is 4. So our horizontal asymptote is equal to 1 over 4 equals y. Now, this is also equal to the limit as x approaches infinity of our function. How do we prove this now? This was the shortcut. Okay? Let that be known. This is the shortcut. How do we do it the proper way? Now, this involves solving limits at infinity has a very mechanical process, in the sense that you need to be familiar with how factoring really is. For example, factoring, these special trinomials or special cases like difference of two squares, or sum or difference of two cubes, or perfect square trinomials, these aren't the same. They don't function that way. To go back to the basic definition of factoring, we're getting the common term across the entire polynomial, and we're trying to divide everything so that we have two factors that multiply to one another. So what that looks like is, if I have x squared plus x, they have a common term of x, so I'm dividing this by x here so that I can get this final answer. Since I divided by x, that means I'm multiplying. X squared divided by x will just be x. X divided by x is 1, so x plus 1. This is how you factor. You're not gonna get rid of the denominator, you're gonna make it your multiplicand. Now, okay, using that understanding, we're going back to factorization, the basic form of factorization. We know that this is supposed to be the final answer, so we're just gonna put this here on the side. I mentioned in the intro video that there is a rule for limits at infinity. It says that for any rational number or real number here on top, for any real number n over any variable raised to a positive real number, this always has to be positive, then the limit as x approaches infinity, will always equal 0. Hold on, this infinity kinda sucks. Infinity. There. So now, using this, basically, what we want to do whenever we're dealing with limits like this is try to force our function into this format. Now, how do we do that? Basically, what we're just going to be doing is we're going to divide and factor out the largest term in both the numerator and the denominator. We're essentially forcing a common term to appear. And in doing so, we can arrive at that form, or we can simplify our function into 0. How does this look like? Okay. So it might be a bit hard to visualize just like that. So let's move this here to the side. We want to factor out x squared on the top and x squared on the bottom. Those are the highest degree terms that we need to get rid of. So we're gonna get rid of the 1 first. We want to get rid of x squared, so we're gonna take out x squared already, and we're gonna do it in the format that we did a while ago. Divide everything by x squared. X squared over x squared plus 16 over x squared. And this is over x squared on the bottom. 4x squared over x squared minus 2 over x squared. And don't forget to rewrite the limit statement. So the limit as x approaches infinity. Now, how do we simplify from here? Let's just get rid of all of the ones that simplify to 1. So we're gonna rewrite it again. We'll get actually, we can cancel these two out. This becomes 1, this becomes 4, and we'll get to the next part after. Okay, so basically this now becomes the limit as x approaches infinity of 1 plus 16 over x squared. What is 16 over x squared in terms of this limit? 16 over x squared in terms of this limit is satisfying this right here, this condition. We have a real number on the top, and we have a variable raised to a positive rational number. So we can also say that this is now equal to 0. 1 plus 0. Now on the bottom we have 4 minus another number that satisfies this condition, 2 over x squared. So since that's also equal to 0, we're now brought here. And since we're already done satisfying our limit through that, we just have to remove our limit statement here. And our final answer for the limit of f of x is, hold on, the limit of f of x as x approaches infinity, that's 8. This is equal to 1/4. Hold on, let's move this here. Okay, there. So we now know that it's equal to 1/4. Now, okay, this process really is kind of it's like a puzzle-ish sometimes. You need to figure out when you can cancel and how you should cancel the numbers. Because sometimes if you cancel too early, then you're not going to get anywhere. And if you cancel the wrong stuff, you will also get nowhere. So, let's try another example. This time, a bit trickier, particularly because we now have a square root, or really any radical. Okay, so the most common that you'll experience in high school is the square root type of function. So let's try another one. Hold on, let me bring this back with me. Hold on, right here. Okay, let's try to get the limit as x approaches infinity. No, this is a different pen. The limit as x approaches infinity of the square root of x to the, let's say, x to the 4th plus x squared, let's make this 5, let's make this 3, 3x squared plus 4. I don't know, and the denominator is just going to be 5x cubed minus 2x plus 1. Okay, now this is a bit different, okay? What we need to do first in tackling this question so that we can get to the form that we want here on the right side is we need to start using our limit laws. And how will we use our limit laws here? First, we have to use the limit law of the quotient of limits. So, hold on, let's use a different pen. Let's use yellow, perhaps. Now, the limit as x approaches infinity of, okay, let's just immediately, or actually no, we won't do that yet. We're just going to put it on the numerator. So 5x to the power of 4 plus 3x squared plus 4 over the limit as x approaches infinity of 5x cubed minus 2x plus 1. Now, before we simplify and we start distributing our limit laws even more, what we need to do first is we're going to start doing our factorization of the top and the bottom, because we cannot get to this point unless it's already been factored out. So we're going to start factoring out underneath the radical first. Now let's try that. So dividing everything by x to the power of 4, we're gonna be going with x to the 4th here times 5, hold on, 5x to the 4th over x to the 4th plus 3x squared over x to the 4th plus 4 over x to the 4th. Okay, there. And then the limit statement is on the outside. The limit as x approaches infinity. There. Now, what we do now is we're going to do the same thing for the bottom. Now the bottom and the top do not have the same degree, so we're just going to do the same process, but this time with x cubed. So the limit as x approaches infinity of 5x cubed over x cubed minus 2x over x cubed plus 1 over x cubed. Now, we cannot cancel out to 0 yet because we don't have our limit statement. So, what we're going to do is we're going to start applying our limit. However, before we get to that, it's important to take note that we actually already have a square here. We're getting the square root of this entire thing. However, now we have a square root. And this is multiplied. So we can take this outside. And that basically makes it so that we now have the absolute value of the square root of x to the fourth, which is just x squared, times the square root of everything else inside. Now we're going to distribute our limit statement again. So the limit as x approaches infinity of 5x to the fourth over x to the fourth plus the limit as x approaches infinity of 3x squared over x to the fourth plus the limit as x approaches infinity of 4 over x to the fourth. Same thing with the bottom. This time, oh, we forgot to put our x cubed here. Okay. Anyways, so we're going to put our x cubed out here, and we're now going to distribute. We're going to get the limit as x approaches infinity of 5x cubed over x cubed minus 2x 2x over x cubed plus 1 over x cubed. Simplifying this with our limit statement here on top, the condition, we can now get the absolute value of x squared times 5. These cancel out. This becomes 0. This becomes 0. So plus 0 over the... Oh, there's no square root here. My apologies. There shouldn't be a square root here. Okay, there. 5 minus 0 plus 0 times x cubed. Okay, there. These are also multiplied. So we can actually cancel this out. We'll be left with 1 over x here. And we'll get the square root of 5 over x times 5. Now, from here, we can see that we're not really done yet. So we have to bring back our limit. We're going to bring back our limit of our now simplified function, which is square root of 5 over x times 5. And we can actually split this into a new statement as x approaches infinity of square root 5 over 5 times the limit as x approaches infinity of 1 over x, which is our product of limits rule, or yeah, our limit law of the product of limits. So this becomes 0, and so our limit as x approaches infinity is going to be 5. The limit as x approaches infinity, following the constant limit rule, is equal to square root of 5 over 5. That was a pretty long question. However, that is essentially the gist of how square roots are going to be taken, how to get the limit of rational functions with radicals for limits approaching infinity. And another important thing to note here, for square roots, the reason why we put this absolute value bar is so that we can adjust the sign based on what sign of infinity we're using. For example, since this is positive, we're just going to use the regular version. However, if it were negative and we were looking for the limit at negative infinity, we'd leave a minus sign here, and we just get the same thing except negative. So that essentially wraps up this in-depth video. Um, Clearly, this is a bit of a. This topic of limits is very mechanical. It's very heavy on factorization, and it's very heavy on making sure that you're doing the right algebra. However, practice is key. That last question here, this question here, it's hard to do if you don't know where to begin. That's why analyze your limit laws, analyze your algebra and how to factor out properly like we did here in the step by step, because these will allow you to solve for the limits at infinity of any function. And of course, learn to analyze. Because in questions like this, for example, this x squared plus 16 over 4x minus 2, 4x squared minus 2 rather, sometimes you don't even need to do all of that. You can use the shortcut. You can get the horizontal asymptote. So this topic is both mechanical and analytical. You have to know what you're looking for. So, without further ado, that is the end of this in-depth concept regarding limits at infinity. Possibly could reappear in some certain topics. However, for now, this is where we're stopping. So I hope everyone learned something, and I hope this video helps. And of course, this topic really is something that requires a lot of patience. So I completely understand if there's any need for clarifications in the comments and etc. Please just let me know. And yeah, that's all. Thank you very much, everyone, and goodbye.